This video is for AP Calculus, Chapter 7, Lesson 4. We're actually going to be beginning about 4 days of all one topic. I've actually seen some teachers do this all in one day. We're going to go kind of slow and spread it out over 4 days. And they're all about these things called areas of cross-section. Not a big lesson today in terms of pages, only 3 pages, 4 examples. In fact, here's kind of all the examples squished together. But they're all kind of relating to the same thing. How do you find the volume of something where you have to slice it up into little bits that are in cross sections, little wafers? And I'm just going to steal this picture here and go back to your notes. So we're on this page right here, and we're going to start off trying to find the volume of this building in Vancouver. It's called the TELUS building. It's kind of right on the border between Vancouver and Burnaby. And it has this unusual shape to it. It's actually, it's often just called the boot because it does kind of look like a boot where it's wider on the bottom and then it's a little narrower as you work your way up towards the top. And we're going to try to figure out a way to do this by summing up a whole bunch of little infinite wafers, infinite little crackers if you wish, in order to come up with a total volume for the thing. Just to help you out with this, I took a hunk of cheese and I actually cut it to kind of look like the TELUS building, to look like the boot. And I just wanted to talk about making calculus cuts and like what would be appropriate cuts and what would be really awkward cuts to do. And if you were to take this weird, crazy volume that a kid in grade 8 or 9 would not know how to find the volume of, if we want to do it, this is probably not the way you'd want to cut it. You could create some individual slices that are very thin, but they would all look like boots. They would all be very tough to find the volume for. There are 2 better directions you can cut it. This way is one, to cut it continually like that, all the way across the boot. It's an option that would work well, but we're actually going to cut it like this, kind of floor by floor on the TELUS building. So after you've gone and sliced this thing, floor by floor, as long as you make your cuts thin, people won't notice that this edge is actually beveled. And if they do notice that it's beveled, well, just cut it thinner. And the neat thing about the calculus is it will cut it infinitely thin. So the challenge really is just once you take one of these floors out, how do you find the volume of one of these little floors? So the whole volume we'll call V for volume. And this is a little elemental volume, a little dV. And if we just tell the calculus, hey, you've got to add up a whole bunch of those little dVs, then we should actually be in business. So that's going to be our plan for this TELUS building. We'll see if we can actually get it to work. So what do we know? The width is 30, every floor is 30 wide. The length of the floor varies, and overall the entire height of the building, once we get up to the top, is going to be 60. I'm just going to take my little picture here, put that over there. If you imagine slicing this thing up the way that we talked about, okay, maybe I'll do this orange, kind of like the little slices of cheese. Then here's one little cheese slice, right, like in here like that. And then there's kind of the dimensions that we can't see going like that. And we have to try to find the volume of that. I'm going to actually be integrating with respect to y. So I'm going to be letting y keep track of where we're at. And then the thickness of the floor will be very thin. That'll be some sort of dy, some small little change in y. At the very, very beginning of the day, when we start this construction project, y will be 0, and we'll know we're done the day when we get to the very top of the building, which we're told in the notes here is 60 meters up. Okay, so all we have to do is just teach the calculus how to find the volume of that little wafer of cheese, and we're totally set. So I'm just going to draw that wafer again, just so I can see it a little bit more clearly here. So it's a nice little rectangle. What do we got? Going kind of like this. Each one's going to have a different kind of length to it across the building. That's fine. Kind of like that. Okay, so each one of these little floors is a little chunk of the volume. It's a dV. I can see from the picture, it does say that the width is always 30 right there. So that means that this dimension for every single floor is going to be a 30. Going this way, it's just a little slab of cheese, right? Going that way, it's dy. And we are told that the dimension this way does depend on your altitude. Okay, it's explained up there in the picture that this is 60 minus the root of 2y. Okay, some function. So as the y goes up, it'll actually end up being a longer floor in that direction. And it is literally this simple. We just tell the calculus, hey, calculus, you got to get busy. You've got to go sum all these things up. So we're going to say, can you please sum the individual little wafers? Okay, so these are volumes of cross-section. So volumes by making little crackers or little cheese slices. We're basically going to say to the calculus, you have to go and add up these dVs. So all we need to do is just teach it how to find a single slab, and then we're totally fine. Well, it's just a little rectangular prism. Length times width times height should do it. So I'm going to put in those 3 different dimensions there. I've got a 30. There's also a 60 minus the root of 2y. And in the other dimension, it's a dy. And you're done. Like that's the whole story. We do know that this thing begins at floor 0 and finishes at floor 60. At this point, you can torture yourself and do that one by hand, but nowhere in there did it say you had to do it analytically. So go ahead, throw it into your graphing calculator. And if you want to, you can even change the y's to x's. Nobody will know. If you want to double check it, I believe the volume should be 94,854.6586. Always got to do our 4 decimal places. Meters cubed, you're done, right? And then you've essentially found the volume of this little stack of little flat wafers of cheese. And by doing that, they're all infinitely thin. We don't have to worry too much about that beveled edge, and everything is great. And then we get to the next couple of questions. The next trio of questions are kind of all the same in some rough way. At first glance, when you read them, most students' reaction the first time they see it is, what is going on? Let's read it here. A 3D solid, so it's a full-on 3-dimensional shape, has the region above the x-axis and below some parabola as its base. Okay, I'm already a little bit confused. And then it gets even more interesting. Cross-sections of the solid cut perpendicular to the x-axis are in the form of rectangles whose height is half as large as its width. It's like, whoa, okay, that's confusing. Looking at all of the examples that we're going to finish up here today, examples 2, 3, and 4, they're all essentially exactly the same. The only difference is what these cross-sections are. At the beginning, they're going to be rectangles. Then we're going to have equilateral triangles, and then we're going to have semicircles. So once we've got this thing dialed in once, it shouldn't be too bad. I am going to steal this little picture from a graphing calculator. I graphed that parabola just to see what it would look like. So I'm going to take that, and I would encourage you to do the same. And just go ahead and drop this, just, some sort of sketch of this into your notes so you've got a picture of it. That's the base. That's the foundation that this building is going to go and sit on. Just looking at the parabola, looking at the numbers here for it. Got one x-intercept at 1, 2, 3, 4, and then another one at 5, and then the vertex is all the way up there at 4, okay, right up there at the top. And that is not the 3-dimensional shape. That's just a 2-dimensional shape. And that's like the foundation, like a slab of concrete that we're going to go and build a 3-dimensional shape on top of. And at first glance, it's kind of hard to imagine what this looks like because we're only drawing on 2-dimensional paper and there's this talk about this 3-dimensional shape. So I thought I'd build you one out of cheese. So here's the plan. I just took a chunk of cheese. And it's 3-dimensional, but it needs to be shaped a little bit. So the first thing I did was I shaped it like that parabola so that it would actually fit kind of on top of this region right here. Because they talk about this region that's underneath the parabola, but above the x-axis. So this slab of cheese needs to sit on top of that little slab. Okay, but it has to be a very carefully constructed chunk of cheese. They said if you cut it perpendicular to the x-axis. Okay, so I have to cut it like this. Okay, making a whole bunch of little wafers all cut with my knife perpendicular to the x-axis. Now when I look at each one of these little cross sections, these little slices of cheese, if I pull one of them out, I have to make sure that it's a rectangle and its height has to be half as big as its width. Okay, well, work with me here because I only have this one thickness of cheese. I wish it was a little bit thicker, but that's that's pretty close to being half as tall as it is wide. But then I looked at the edges and went, well, no, if I'm going to say the middle one is half as tall as it is wide, then these ones on the edges, they're too tall. So I cut them a little bit and then just discarded the pieces that I didn't want. And I actually continued to do that for all of them. So I went and took each piece and said, all right, let's cut them so that their heights change, because their widths are going to change when you look at them as rectangles. And then when I was done, I ended up just kind of bunching it all back together, and that's the shape. So it's three-dimensional. It's a big chunk of cheese, and it can sit on top of that foundation that's under a parabola and above the x-axis. And I've sliced it perpendicular to the x-axis, and each one of these little chunks of cheese is supposed to be, when you look at it on the side, in cross-section as we say, it's supposed to be a rectangle. And then what we need to do is tell the calculus, hey, for this little rectangular cross-section, what's the volume? And if you cut it thin enough, you won't even notice the bevel up here. That's the cool thing about the calculus. Then we have to go and teach the calculus how to find the overall volume. So if you haven't sketched that shape, you probably want to do that. And now what you have to imagine is standing on top of that shape are a whole bunch of little slabs of cheese, right? Like here's one of them. Okay, it kind of sits here, kind of like, I don't know, kind of like this. And when I look at it like that, it's a rectangle, and it's supposed to be half as tall as it is wide. Okay, so I need to pull this little slab of cheese out a little bit more. I can't quite focus on it here, so I'm just going to extract it a little bit where I can see it a bit better. Okay, so there's the cross section. Yeah, it does look like a rectangle. There, it's a little slice of cheddar cheese. And now what we need to do is teach the calculus how to find that volume. And each one of the volumes is a little bit different, right? Depending on where they're located. So if you think about where they're located, this is kind of like x is the axis going this way, and then dx is how wide each one is. And it does depend on your x location to figure out exactly what the dimensions of this shape are. So this is a dv. We just have to add them all up. And they're located at some particular x value, and their thickness is just going to be that small little change in x. That's going to be dx. But now the other dimensions. Well, I can see that it extends from the x-axis, which is like y equals 0, all the way up to that parabola. So if you think about how big it is this way, that's exactly the height of the parabola. That would be this negative x minus 3 squared plus 4. That's that dimension, because that's the y value for this line right here. And then the x-axis, of course, is y equals 0. So I'm just taking the parabola and subtracting off 0. Then they said, oh, these are going to be rectangles, but they're not quite as tall as they are wide. So this height here, going this way, they said, don't worry, we'll give you some advice. It's going to be 1/2 of this number, right? Kind of like the width of it, but only half as big. Okay, so here goes. We're going to go and add up all these things here. That volume, it's going to be the sum of a whole bunch of little dv's, right? That's the plan. We just have to teach the calculus how to find that little volume of cheese. Well, it's just a length times a width times a height. So here goes one of the dimensions. It's just that parabola. Negative x minus 3 squared add 4. There. That's how big it is this way. Okay, so I've got that. Now I got to put in there, how big is the thing this way? Well, same number, but only half as big. Okay, so I'll put in times 1/2 of, and I'll just repeat it. Not quite a volume yet, that's only an area. But if I multiply by how thick the little piece of cheese is, the dx, then I'm in business. Now, last thing, looks like x is in charge, so I need to go and put in some x values here and here for where we begin and where we end the story. Looks like the very first x, the very first slice of cheese, happens right here at x is equal to 1, and the last one is at x is equal to 5. So you put in a 1 and a 5, and you're done. Doesn't say to do it by hand. Good thing too, it'd be a bit of a mess. You'd have to probably expand it first. So I would throw it into my graphing calculator. I tried that out. If I haven't made any mistakes, I got 17.0667. I don't know, whatever the units are, some sort of dimensional units cubed. And you're done. The only difference with the last two questions are the shapes. They're no longer rectangles. They're going to be some other weird ones. So looking at the next example, they're talking about making not rectangles, but what if we make triangles? In fact, they say equilateral triangles. So we'll just have to figure out, like, how would you find the volume of a little triangle like that? And the example after that, the last one we'll do is semicircles, right? So we just have to teach the calculus, how do you find the volume of a little equilateral triangle of cheese? Like exactly like the shapes you kind of see at Subway, right? They're throwing on your sandwich. And what about little half circles of cheese with some thickness to them? If we can get that dialed in, then we're totally good. Okay, so last two examples, last page here. Same story again, but this time you have to, when you cut them, you have to end up with these equilateral triangles. Okay, no big deal. We should be able to pull that off. So it's generally the same plan. There's still this space where you're supposed to build this structure. It's underneath a parabola and above the x-axis. But now when you build these little slabs of cheese, they're supposed to be equilateral triangles, kind of look like that. And the triangles get bigger, of course, when you get near the apex of that parabola. Okay, so this really isn't going to be too much of a calculus game. It's more of like a Math 11 special angles game than anything else. Just figure out all the dimensions here for our rectangle, and then we'll be good. All right, along the base of this triangle, because I know for triangles you're generally supposed to go, 1/2 times the base times the height of a triangle. Okay, so the base could be here, and it's just that distance between the parabola and the x-axis. So that's easy. That's like that negative x minus 3 squared plus 4. But then I'm going to have to figure out, just with some math here, how big is that height? And then the thickness is easy. It's just dx. Kind of been playing that game for a few days here now. Okay, for the height, well, it does say equilateral triangle, so I do know that all of the triangle's corners are 60 degrees. What I could do is say, hey, this side right here, if it's equilateral, they're all the same length. This is also minus x minus 3 squared plus 4. This is not the only way to do it. But I'm going to relate this hypotenuse in here to that height for the little triangle of cheese. And I can do that one. If I kind of twist my head sideways, I can think of the hypotenuse on that 60 degrees, and the height of this triangle is opposite that 60 degrees. So I can actually use sine, right? I could say, okay, sine of 60 degrees would be the opposite, which is h, divided by that hypotenuse, divided by basically this number going right there. Okay, now we're ready to roll. The volume, gonna sum up a whole bunch of little dv's. Gonna be integrating. I'm gonna go thinking about the equation 1/2. Okay, so 1/2 for a triangle times the base. Okay, here comes the base. Negative x minus 3 squared, add 4. 1/2 times the base times the height. The height would be that length again. Multiplied by the sine of 60 degrees. And one more dimension, dx. Done. Taught it how to do it. I can also see that x is in charge. The very first x where a slice of cheese shows up is 1, and the last one is 5. Done. I don't even know what the answer is. I don't even care. Neither should you. It's the setup that's more important, right? Just kind of teaching the calculus how to find the little incremental pieces that will add up. The last one, number 4, same region, same kind of foundation of concrete that we're building this cheese house on, right? It's got to be above the x-axis and under that parabola. But this time, as you go up into the air, the little slabs of cheese are supposed to be these semicircles. So we'll just have to teach the calculus how to find these semicircles. And I'm just going to draw a slightly bigger semicircle here. Okay, here's a little semicircle of cheese. Like that. I can see that the diameter, I'm going to be careful because a lot of my formulas for area work on radius, but the diameter would be this negative x minus 3 squared add 4. And the thickness of the cheese is going to be dx. Okay, so that's all good. And now I'm just going to do the area of a circle. I'll cut it in half, so I'm going to go like 1/2 pi r squared to find the area of that circle, right? The area of the half circle, multiply by the dx. I'll be done. So for this one, again, you want to let the calculus work for you, not the other way around. So just say, hey, calculus, I got a job for you. Got to add up these little dv's. So let's go teach it how to find a little volume of cheese. So I want to go 1/2 because it's only a half circle. So 1/2 pi, and I want to go radius squared. So the radius, well, if I take this would be the diameter. And it's the diameter of that chunk of cheese. What I could do is I'll just take that diameter and cut it in half. There. Now that's a radius. Square it. There. I just taught the calculus how to do it. And it's my calculator's problem after that. It's going to have to sort out all the brackets and figure out where everything goes. That's not quite a volume yet, not until you multiply by the dx. And again, that dx, right, the fact that there are x's here says, okay, x's are in charge. Where's the first chunk of cheese? Where's the last chunk of cheese on the x-axis? Well, the first chunk is at 1, and the last one is at 5. So we're doing these areas of cross-section where we're imagining taking this volume. It's a 3-dimensional shape, and we're taking it and we're slicing it up into a whole bunch of little beautiful little cross-sections. And maybe the cross-sections are rectangles, maybe the cross-sections are triangles, maybe they're little semicircles. But we just have to teach the calculus how to find the volume of each little one. And if we cut them fine enough, like calculus does, you don't even notice that the edges are curved. And then there's really just 2 problems left. Number 1, throwing it into your calculator. And 2, trying to figure out what you're supposed to do with all this extra cheese. So once you've dealt with that problem, then everything's good to go. So that finishes up our lesson for today for this 4th day of Chapter 7.